In this lesson, we'll be studying data variability, comparing data about two populations by using measures of center and measures of variability. You're familiar with measures of center, even though you might not recognize the term. The mean, or the average, and the median, the middle number, are measures of center. And measures of variability we're going to get into in this lesson. Alright, a box and whisker plot uses 5 points on a number line to summarize a data set. Well, we said box and whisker. Box and whisker. Let's look down here. Here's a box, and it has whiskers. So that's why it's called a box and whisker plot. It says it uses 5 points of data on a number line. So there's 1, 2, 3, 4, 5 points on the number line that they're going to use. And so it's divided into 4 quarters or quartiles, okay? Here's the first quartile, and there's the number that represents the end of it. There's the second quartile, and the median is that one. The third quartile, quartile 3, and finally the fourth quartile. The ones that you're going to be most that are going to be used most often are quartile 1, quartile 3. All right, the interquartile range, the IQR, you'll call it that. That's how you'll write it. You'll still say interquartile range every time. Of a data set is the difference between the upper and lower quartiles. Okay, the upper quartile, let me get a marker here. All right, the upper quartile is quartile 3. And as you see here, it's 44. The lower quartile is about 23. And it's the difference between the two. So the interquartile range of this data set is 21. Okay, let's move on. The interquartile range is one measure of variability which shows how much a data set is spread out. Okay, there we go. All right, so in this circumstance, it's spread out from 23 to 44. Now, how do you use that kind of information? A veterinarian collects data about the weights of dogs that she treats. Compare the interquartile ranges of the data sets to draw an inference about the dogs. So we've got two different types of dogs here, an Australian Terrier and a Boston Terrier. And if we compare the interquartile ranges of the two, we've got the Australian Terrier is at 14 for the quartile 3 and 11 for quartile 1. So we go over here and we go 14 minus 11, and that gives us 3. So the interquartile range is 3 for the Australian Terrier. For the Boston Terrier, we go from 20 for quartile 3 to 17 for quartile 1, and we have an interquartile range of 3. So what does that tell us? What kind of inference can we make? Well, the interquartile ranges of the data sets are very much the same. So you can infer that the weights of Boston Terriers vary about as much as the weights of Australian Terriers, because that's what that box tells you, is how much does the weights of the Boston Terriers vary, and how much the weights of the Australian Terriers vary. Sometimes this box will be very long, sometimes it will be short. The shorter it is means the less amount of variance that there is. Okay, compare the medians of the data sets in the box plots and use the comparison to draw another inference about the dogs. Well, let's look at the medians. The median weight of a Boston Terrier is 19 pounds. The median weight of an Australian Terrier is 13 pounds. So what kind of inference could you make about those two dogs, those two types of dogs? Yes, you can make even though some, so you can see here, even though some Australian Terriers are bigger than some Boston Terriers, on the average, a Boston Terrier is going to be bigger than a Australian Terrier. All right, now the difference between a measure of variability, such as interquartile range, and a measure of center, such as the median. The measure of center indicates the typical value in a data set. The measure of center, like the average, or the average, mean, or the middle number, okay? A measure of variability indicates how spread out the values are in the data set. Let me go back 1 second here. The measure of center would be right here, the median, okay? The median, okay? That's the measure of center. The box is the measure of variability. Okay, this box and whisker plot shows the heights in inches of the players on a women's college basketball team. What are the median and the interquartile range of the data? Well, as we look here, remember the median is the number that's inside the box here. So the median is 73. And the interquartile range is just quartile 3 minus quartile 1. So that will be 74 minus 70, which gives us 4 for the interquartile range. So the median is 73 and the interquartile range is 4. All right. This box and whisker plot shows the prices of shirts at store A and store B. Compare each pair of measures for the data sets in the box and whisker plot and use each comparison to draw an inference. Let's look at it. We've got store A. Look at this now. See what I tell you about the box. The box indicates the variance, the variability of the data information, okay? So on this box, it's very large, very long. This box is short. So what does that tell you about the information? Yeah, it tells you about the information in store A. The shirts are going to vary. The price of the shirts are going to vary a lot. And in store B, they're not. So let's look at and see if what we find out it supports that. The median price in store A is how much? It's $24. And the median price in store B is how much? $38. So what inference could you make about the two stores? Well, you can make the inference that the shirts in store B are generally more expensive, or about $14 more expensive than shirts in store A. All right, in the interquartile ranges, let's look at store A again. Store A, the interquartile range is going to be 35, quartile 3 right here, minus quartile 1, so 35 minus 20, which is 15. And store B is going to be 42 minus 33, which would be 9. So what do those interquartile ranges tell you? In store A, there's a variance of $15 between those two in the interquartile range. That means their prices on shirts vary a lot. Whereas in store B, the prices of shirts are more consistent, okay? A second measure of variability is the mean absolute deviation, or the MAD. Hey, that makes sense, doesn't it? Mean and MAD. The MAD, or the mean absolute deviation of a set of data, is the average distance between the mean and each data value. Oh my goodness. We're going to need to practice this because that sounds complicated. You can determine the amount of overlap of two data sets by expressing the difference between their centers as a multiple of the MAD, or the IQR, mean absolute deviation, or the interquartile range. A multiple of less than 1 indicates a large amount of overlap. A multiple greater than 1 indicates a small or no amount of overlap. So let's see what we can find out about this. I know this has been confusing just reading this. But let's see what we can do about understanding it while we do it. The data table at the left shows the number of points scored by each player on two basketball teams during a game. Use the measures of center and variability to express the amount of overlap between the data sets. Now we're going to do what we just talked about doing, so let's concentrate on being able to understand what it is that's taking place here. So we're going to calculate the mean of each set of data. So we come over here, and they had one player who scored 4 points. They had two players who scored 6 points each, that's 12. Two players who scored 7, so that's 14. One player who scored 8. And two players who scored 9, so that's 18. We add those up, we get 26, 40, 56. Now how many players were there? There were 1, 2, 3, 4, 5, 6, 7, 8 players, so we divide by 8. And 56 divided by 8 is 7. So the mean of the Eagles' scoring is 7 points. Now we come over to the Vikings. The Vikings had two players who scored 0. So we don't put down anything. They had one player who scored 1. Two players who scored 2 points, that's 4. One player who scored 3. And two players who scored 4 each, so that's 8. So we have 8, 11, 15, 16. How many players did they have? 2, 3, 4, 5, 6, 7. They also had 8 players. So their average is 2, or their mean is 2. So we've calculated the mean of each set of data. Now what was that? That was the measure of center. Okay, the mean is the measure of center. Step 2. We want to calculate the mean absolute deviation of each set of data. So these are how many points each player scored. Okay, say 4, 6, 6, 7, 7, 4, 6, 6, 7, 7. And we calculated the mean to be 7 each time. Okay, to be 7. So we put 7 down every time. And then we come over here and we try to figure out the difference between the two. Okay, the difference between 4 and 7 is 3. Now say 4 minus 7 is negative 3. But that's why it says mean absolute deviation. Remember, absolute value is always positive. The difference between 7 and 6 is 1, 1, 0, 0, 8 minus 7, 1, 9 minus 7, 2, and 9 minus 7, 2. So we've calculated the distance between the points that each player scored and the mean of the team, okay? The average that the team scored. When we do the same thing for the Vikings down here, we get a difference of 2, a difference of 2, of 1, of 0, of 0, 1, 2, and 2. Now, to calculate the mean absolute deviation, we take the 3 plus 1 is 4, 5, 6, 7, 8, 9, 10. We get a total of 10. We divide it by 8 players, and we get 1.25. So 1.25 is our mean absolute deviation for the Eagles. Now let's calculate it for the Vikings. 2, 4, 5, 6, 7, 8, 9, 10. So we go 10 divided by 8 players, and once again we get 1.25. So the mean absolute deviation for the Eagles is 1.25, and for the Vikings is 1.25. Our next step, what multiple of the mean absolute deviation equals the difference between the means? Okay, let's see. This tells us that the mean absolute deviation times a number, which will be the multiple, is equal to the difference of the means. Okay, so the mean absolute deviation was 1.25, times n, that's what we're trying to find out, equals the difference of the means. The difference of the means. So we come back over here to the means. The mean was 7. The mean was 2. So what's the difference between 7 and 2? Right, that's 5. So we go divide by 1.25, divide by 1.25, and that gives us 4, that gives us n. Let me get rid of that. That gives us n equals 4, because 5 divided by 1.25 is equal to 4. Now what does that information tell us? Remember, let's go back over here just a second. You can determine the amount of overlap of two data sets by expressing the difference between their centers as a multiple of the mean absolute deviation. Okay, we did that and we got a 4. A multiple less than 1 indicates a large amount of overlap. A multiple greater than 1 indicates a small or no amount of overlap. Well, we got a 4. So what does that tell us? That tells us that the data sets have no amount of overlap, or a small or no amount of overlap. Now let's look back over here and see. Look at the information here. The only place they overlap is right here in this information with the number 4, 4 points scored. So the 4, that was our mean absolute deviation, indicates that there is small or no amount of overlap. And if we look at the information here in a chart, we can see that they have almost no overlap, just one place that they have overlap of data.